Hey, AP Physics, Mr. Nunez here. And what I want to talk about in this quick review, it's probably not going to be quick, is the motion graphs that we talked about in class today. And so what I've done is I have created every possible scenario that we could plug into our little simulation here. I'm going to run it, show what the man does, and then I'm going to explain some of the key features of what's going on. Okay? So in our first scenario, our position, velocity, and acceleration are all going to be set to 0. So you can see I have position, velocity, and acceleration all set to 0. Now let's go ahead and hit play and see what happens. And this is perhaps the most boring graph that we could look at. No matter how long I let this run, you are just going to see this flat line propagate down here on the bottom, okay, in all three places. And so if we were to come up with a description for this, we would say the man is not moving. That's the very simple description. And we could also say all of the graphs are flat, meaning constant, at a value of 0. Okay, so this is telling us that as the stopwatch moves on, his position is 0 at all points, his velocity is 0 at all points, meaning he's not moving, and his acceleration is 0 at all points, meaning his velocity is not changing at all points. Next, what I want to go ahead and do, and I'm just setting this down to 0 for ease of view later, is we are going to look at a positive position, 0 velocity and 0 acceleration. So let's set his position to a positive value of 5. We'll clear everything so far and we'll hit play. And you can see as time goes on, we have more flat lines, still more boringness, okay? And what we could say is the man is not moving, but we can get more specific. We would say that he is standing on the positive portion of the ruler. Okay, so he's over here on the positive side. And we could also say all of the graphs are flat, which means that they're constant. And the position is at a value of 5 meters, but the velocity and acceleration are at a value of 0. Okay, velocity would be 0 meters per second. Acceleration would be 0 meters per second squared. Now I'm going to set his position to negative and leave the other two as 0. And if we do that, let me go ahead and type that in. We'll clear the graphs. You can probably predict in your mind using our pattern what is going to happen. Hopefully in your mind you were thinking, well, all we've changed is that he's on the negative side of the graph now. So we would say the man is not moving, but he is standing on the negative portion of the ruler. Okay, so all this depends on is where we set our 0 point on the ruler. So because we set the 0 right in the middle, when the position was positive, we just meant he was right of 0. And when the position was negative, he was left of 0. But the rest of this we can copy and paste from our last description because they're all flat and constant. The only thing that changes is that his position value is now, see if I can get my cursor there, is now negative 5 meters. Okay, so those are the easy ones, no motion. Now what we're going to do is we're going to start our man at a position of 0, but we're going to introduce a positive velocity. So let's put his position back at 0, and I'm going to give his velocity 1. And let's run this and see what happens. Okay, so now he's moving. Pretty simple. Let's go ahead and take the walls out of here. And as this run, we can now say the man is moving, and we would say that he is moving in the positive direction. Okay. And as he keeps going past 10, we see our graph keeps climbing. If I zoom out, you can see it goes up to 12, and it'll just keep going. Okay. Now, if I play it back, one of the things to note is the position graph has a y-intercept of 0, which tells us that at time 0, when our clock says 0 here, he was at the 0 position on the ruler. but our velocity was always 1. So from the very beginning, he was moving. Now, because it's 1 meter per second, what we should be able to see is that at every second mark, so at 1 second, he's moved 1 meter. So here we go. Let's move this over to where the clock says 1 second. And sure enough, his position is about 1 meter. At 2 seconds, we see his position is at exactly 2 meters. At 3 seconds, he's at a position of about 3 meters. And that trend will continue forever. Okay, so this is telling us the meaning of our velocity is that every second he moves 1 meter. And so if we were to calculate the slope of this, okay, let's look at a time of 6. Okay, he's moved 6 meters in 6 seconds. So delta y over delta x, 6 meters in 6 seconds, he has a velocity of 1. So the slope of this graph represents the velocity as 1. We could check this at a time of 4 seconds. Okay, his position is 4. So we have change in position of 4 over change in time, which is 4, which means even here his velocity is 1, and that matches up with this graph. But we could jump to the end. We could look at 10 seconds. His position is 10. 10 divided by 10, so 10 meters in 10 seconds means his velocity is 1, which is what we see on the graph here. So we could say the position time graph, and I'm just going to call it xt, the position time graph shows a constant increase or a constant change of position of 1 meter every second. Okay, it crosses the y-axis at 0, that's where he started, and the velocity graph shows a flat or constant line value at 1 meter per second. And then because our velocity does not change, we could also say that the acceleration is 0, and sure enough, that's what we see on the graph here. The acceleration is a flat line, which means it's constant at 0. We can also prove that by taking the slope of the velocity graph, okay? So let's say this is y2, okay? So we have our velocity of 1 at a time of 2. So if I were to write this out, I can't write it out. So you'll just have to follow along with me. We got y2 minus y1. So the y value, which is our velocity, is 1 over x2, which is 2. So we've got 1 over 2 minus, our velocity is still 1 over 0. So on the top, we would have 1 minus 1. On the bottom, we would have 2 minus 0. So that would be 1 minus 1 is 0, divided by 2 minus 0 is 2. 0 divided by anything is 0. And that tells us that the slope of our velocity graph is 0, and lo and behold, our acceleration value is 0. So the slope of our position time graph is equal to the value on our velocity time graph, and the slope of our velocity time graph is equal to the value on our acceleration time graph. Let's look at the next scenario. Positive position, positive velocity. So let's put him at a position of 5 meters again. Let's keep him at a velocity of 1, and let's hit play. Okay, sure enough, he's moving to the right. Let me kick those walls out of there so we can keep on going. And there he goes off into the distance. So again, we would say the man is moving in the positive direction, but we could also say that he started from a position of 5 meters. Okay. Everything else, though, is exactly the same. If we were to look at this, let's see if I can play it back. Okay. So at 2 seconds, he was at a position of 7 meters. Okay. Let's even back further up. So at a position of 0, or at a time of 0, he was at a position of 5. So when the timer started, he was already at 5. 1 second later, he was at a position of 6. Another second after that, he was at a position of 7. Another second after that, he was at a position of 8. So his velocity is still 1 meter per second. The slope of this line is still 1 meter per second. We just shifted it up to represent that he started at a position of 5 meters. So I could literally take the explanation from the last scenario and I could plop it down here. The only thing I would change is that it crosses the y-axis at 5 meters. So what this tells us, on the position time graph, the y-axis, the y-intercept, shows us where he started. In the previous scenario, he started at a position of 0 and the y-intercept was 0. In this case, he started at a position of 5 and the y-intercept was 5. So now we're going to start him on the negative portion of the graph. Let's set this to -5. We're going to keep his velocity positive. Our acceleration is still 0. Let's clear and hit play and get the walls out of there. Okay, look at this. As it propagates, we are doing the exact same thing. Okay, and if we let this run for a while, our little man here is just going to keep on trucking. So our description of his motion, we can basically copy and paste from above. He's moving in the positive direction, but he started from a position of -5 meters. We also can copy and paste the bottom part. Let's prove that. Okay, if I play it back, he starts at a position of -5. 1 second later, he's at a position of -4, so he's moved positively 1 meter. 1 second later, he's at a position of -3, so he's moved another meter, and so on. So we could say everything from above is exactly the same. The only difference is he crosses the y-axis at -5 meters. Because again, we changed that starting position. We shifted our line down. Now, one more interesting thing happened, and we call this interesting. Whenever a line or a curve crosses the y or the x-axis, we want to analyze that and understand what it means. So acceleration obviously didn't cross the x-axis. It stayed 0. Velocity didn't cross the x-axis. It stayed at 1 the whole time. But our position graph did cross the 0 point. It crossed the x-axis. All that represents is when our man was at our artificial position of 0 on our ruler. So based on our starting point, this 0, at this time, he was right at that position of 0. And it makes sense. He started at -5. 5 seconds later, he would have moved 5 meters. So if he started at -5, he moved positive 5 meters, he should be at a position of 0, which is exactly what we observe here. Okay? So now what we're going to do, we're going to start him at a position of 0. Let's clear everything. Start him at a position of 0. This time we're going to make his velocity negative. Oh, negative velocity. Okay, so we're going to let this run, and we can see that this looks basically the same as last time, only instead of our line increasing on our position time graph, it looks like it's decreasing. Now, we have to be really careful with that word decreasing, okay? Because it's not like his position is decreasing. His position is actually increasing because he's getting further away from 0. And so this is where math and physics are a little bit different. In math, we would say the line is decreasing. That's not wrong. But what we really mean to say in physics is that it is increasing in the negative direction. I know, physicists always have to be difficult. It's increasing in the negative direction because he's getting more negative over time. He's still moved quite a bit, but he's moving in the negative direction. So if we play this back and look at where he was, he started at a position of 0. 1 second later, he's at a position of -1. A second after that, he's at a position of -2. A second after that, he's at a position of -3, and the trend continues. So if we were to take the slope of this line, it goes over 1, down 1, over 1, down 1. That's a velocity of -1. And look at that. If we look at our velocity time graph, it's now a flat line, not at +1, at -1 to match up with our position time graph. So we can basically copy paste everything we said above with 0, +0, but we have to make a few things. a few changes. The man is moving in the negative direction. Okay. We would say the XT graph shows a constant increase of position of -1 meters every second. Now, see, I'm still saying an increase of position of -1 meters. So we could call that a constant negative increase. Okay. We'll talk about what it means to decrease in just a second. Okay. So he has a constant negative increase of position of -1 meters every second. He crosses the y-axis at 0 because he still started at 0. And the velocity graph shows a flat constant value at -1 meters per second, which is exactly what we see here. The acceleration is a flat line at 0. His velocity is still not changing. Okay, halfway there. Positive position, negative velocity, 0 acceleration. Let's run it again. You're probably starting to get bored. At this point, we see that the line is going. The position time graph is going down. We see that the velocity is still a flat line at -1, and we see that the acceleration is 0. But this is where things start to get a little bit more interesting, kind of like when our position was negative and our velocity was positive. We have this interesting point now where the line on the position time graph crosses the x-axis. And like I said, that is always considered an interesting point. So again, we can copy paste most of what we already wrote. The man is moving in the negative direction. But I want to highlight a few things, okay? So he's moving in the negative direction towards 0. Okay, so between a time of 0 and a time of 5 seconds, he's getting closer to 0. This is what we call a decrease in position. Okay, he's moving in the negative direction, but from time 0 to time 5, his position value is decreasing. Okay, so let me write that and then I'll explain why. From 0 to 5 seconds, his position is decreasing. Okay, in physics, decreasing specifically means that you're getting closer to 0. So from 0 seconds to 5 seconds, he's getting closer to 0. So we would say that his position is decreasing. But then after 0, he's now on the negative side of the ruler. So we would say his position is increasing in the negative direction. Okay, we can see that this blue line is getting further from the 0 value on the x-axis. So we have a decrease to 0, and then we have an increase in the negative direction. No matter where you take the slope on this line, you will always get a velocity value of -1. And because the velocity does not change, the acceleration is 0. So let's make a few edits here. We would say the XT graph shows a constant negative increase of position of -1 meter every second. That is true. Okay. The thing that I would change here to be a little bit more specific is we would say the XT graph shows a decrease in position to 0 meters for the first 5 seconds. Okay, and that's representing the fact that for those first 5 seconds, his position was decreasing to 0. Then increased by -1 meters every second after that. Okay, so I say it decreases as he got closer to 0. It increases as he gets further from 0. We would just say he increased his position in the negative direction. We could say it crosses the y-axis at 0. We also would want to highlight it crosses the x-axis at 5 seconds when the man was at a position of 0 meters. The velocity graph shows a flat constant value at -1 meters per second. That hasn't changed, and the acceleration is a flat line at 0. Okay, so this is probably the most confusing part. We see this decrease in position as we get closer to 0, and then an increase in the negative direction after that. Okay, let's throw some acceleration into the mix. We're going to start with, before we throw acceleration to the mix, let's put him at a negative position, so -5, a negative velocity of -1, and let's hit play now. Okay, so he's starting on the negative region. He's going away from 0. So we see this -5 starting point. If we took the slope of this line, it would be -1, and his velocity is -1 to match up with that. Because his velocity is not changing, his acceleration is 0. So this is basically the same thing as when both of those signs matched. The only thing we need to change is he's moving in the negative direction, but he started from a position of -5 meters. And we would say that the xt graph shows a constant negative increase, or increase in the negative direction, of position by -1 meters every second. That tells us that his velocity is to the left. He's going in the negative direction. We could say that it crosses the y-axis at -5 meters. That's where he started. And this will never cross the x-axis because he's heading away from 0. This x-axis represents a position of 0, and he's never going to cross that. The velocity graph shows a flat constant value at -1 meters per second, and the acceleration is a flat line at 0. So there, that handles all of our scenarios where he has a constant velocity. Now we are going to throw in some acceleration. So let's set his position to 0. His velocity is +1. Actually, let's set his velocity at +5. Let's leave it at positive. Yeah, let's set it at +5. Let's set it at 0. Okay, fine, I'll set it at 1. You convinced me. And we'll also set his acceleration at 1. Okay, here we go. Let's clear. Let's hit play. Okay, now all of our graphs are doing something different. It might be a little bit hard to tell right now, but if we look really closely here, okay, this is not a straight line. This is a curve. Okay, in class we talked about this is half of a parabola. We see this curving up motion, and you could imagine that I could draw another parabola on the other side. Our velocity also is not the same. The velocity is going up. Okay, it's not a flat line anymore. It's actually increasing, but it is straight. It's straight up, but it is not flat. And now our acceleration is still a flat value, but it's not at 0 anymore. Now our acceleration has a value of 1. So let's play this back. Let's look at what this man does one more time. Okay, he's moving. He's moving. It looks like he's moving a little bit faster, a little bit faster, a little bit faster, a little bit faster. Let's prove he's moving faster by playing this back. At 0 seconds, okay, he's at a position of 0. At 1 second, he is at a position of about 1.5. I move that over one more. He's at a position of 1.5. Okay, so if you look, his velocity is now 2. Remember, we started him at a velocity of about 1. It should be 1, but can't let me go over anymore. So we started him at a velocity of 1. 1 second later, he is now at a velocity of 2 and a position of 1.5. So in that first second, from 0 to 1, he moved 1.5 meters. If he had a constant velocity, every second, his position should go up by 1.5 meters. So at 2 seconds, his position should be 3 meters. Let's see where he's actually at. If I move this over to 2 seconds, his position is actually at 4 meters. So he went further than he would have if he had a constant velocity. And that makes sense because if we look at the velocity, it went up again. So at time 0, it was 1 meter per second. At time 1, it was 1 meter per second. At time 2, it's now at 3 meters per second. We'll go over one more. So remember, he first went 1.5 meters. This time he went 2.5 meters. So at 3 seconds, he went from a position of 4 to a position of 7.5. So he actually went up 3.5 meters. So the rate at which he's changing position is increasing. And that's because, as we can see at his velocity is increasing, but the rate at which his velocity increases does not change. Every second, his velocity goes up by 1 meter per second. He started at 1 second later, he was at 2, 1 second later, he was at 3, 1 second later, he was at 4. If you take the slope of this velocity time graph, you get an acceleration of 1. The slope of the velocity time graph is the value of the acceleration. And so because the acceleration is always 1, the velocity will always go up by 1 meter per second. Okay? How would we describe this? The man is moving in the positive direction, but the rate at which he moves is increasing. I'm going to put in parentheses here, speeding up. Okay? I'm going to break these out. Let's describe this xt graph. We have a parabola opening up. Even though it's a half parabola, we still call that a parabola opening up. The rate at which the position changes increases by 1 each second. By 1 meter each second. Okay, notice I was really clear here. I didn't say his position increased by 1 meter each second. I said the rate at which the position changes increased by 1. So he started at 0. He was at 1.5 after 1 second. 1 second later, he was at 2.5 or 4. So that means he moved 2.5 meters. At 3, he was at 7.5, which means he went up 3.5 meters. Then he would go 4.5, 5.5, 6.5. So the rate at which his position changes is increasing. Okay. On the VT graph, velocity time, we could see a constant, or we would see a linear increase in the positive direction. Slope of the line is 1 meter per second. Okay. We also would say that it crosses the y-axis at a value of 1, which tells us that at the beginning, okay, when time was 0, his velocity was 1. And that's true. That's what we set it to. So we would also say it crosses the y-axis at a value of 1. And finally, AT, our acceleration time graph. In our AT graph, the line is flat, which means constant, but it is constant at a value of 1 meter per second, or meters per second squared. I'll go ahead and add units to that. Okay. Just a few more scenarios to go. Let's take a look now if our position, velocity, and acceleration were all positive. Hopefully at this point, you're starting to be able to make some predictions as to what's going to happen. Here we go. This one's going to be a little bit harder to see because I can't zoom this graph out. I'm going to see if I let this run for a little while, if I can let it. Look at how quickly these numbers are starting to go. After 5 seconds, he's moved 25 meters. After 7 seconds, he's already up to 35 meters. Look at how quickly his position is changing. Okay, let me see if I can zoom in at all. Disappointingly, it does not let me zoom out on our position time graph. But what you can see, hopefully, is that this is a very slight curve. Okay, so we're just looking at a chopped off piece of that top opening parabola again. Our velocity still started at a value of 1, and it had a constant increase, and it had a constant increase of 1 every second. So we started at 1, 1 second later we're at 2, our acceleration was 1. 1 second later we're at a value of 3, our acceleration is still 1. So you can see the velocity is increasing, the acceleration is increasing. So the only thing that changed was the fact that his position time graph crosses the y-axis at 5. So we would say in our xt part, the y-intercept is at 5 meters. That's where we plopped it in. Okay. We could add that to the description of his motion too. We also could say that the man started at 5 meters. Okay, here we go. Let's clear it. We're going to start with a negative position, positive velocity, and a positive acceleration. All this is going to do is make things a little bit more clear for us. But you should hopefully in your mind right now be able to predict what's going to happen. Lo and behold, we see that our velocity is constantly going up, our acceleration is flat at 1, and this is an even more clear picture of that half parabola, just the side that's going up. Okay, so again, everything is exactly the same. We would say that the man started at negative 5 meters, which means that the y-intercept is at negative 5 meters. The slope of the line of the VT graph is still 1, and it still crosses the y-axis at 1 because that was our starting velocity. We can see that the acceleration time graph has a flat constant value of 1. Okay. Now, just to throw it in here, just to do my due diligence, let's say his position was 5, his velocity was -1. Nah, let's just keep moving. So next, position of 0. Velocity should be positive. We'll set it to a positive value of 1. And we're going to set now our acceleration to a value of -1. And in fact, I'm going to increase our velocity here just to make this a little bit more interesting for us. So here we go. Let's see what happens. Okay, we have some interesting things going on. Here goes our man. Our position time graph is now off the chart, but our man isn't quite leaving the screen. It looks like he's stopped. Oh, he's now coming back. Oh, and look at that. We can see our position time graph again. Okay, our position time graph is now crossing the x-axis, and there goes our guy off into the negative direction. So let me pause it there, and let's highlight a few things. I'm probably not going to type the next 3 out because there's a lot to say, so you'll just have to listen to my words. Our position time graph had a y-intercept of 0, and that makes sense because our man started at a position of 0. Our velocity we set to a value of 5, so the y-intercept of velocity was 5. Okay? What we would say at the beginning is that the velocity was decreasing. Remember, like I said with position, decreasing means you are getting closer to 0. And so we saw that he started at a velocity of 5. 1 second later, he's at a velocity of 4. 1 second later, he's at a velocity of 3. 1 second later, he's at a velocity of 2. 1 second later, he's at a velocity of 1. And 1 second later, he is at a velocity of 0. Okay? Now, this is an interesting point. Remember, whenever something crosses the x-axis, it's interesting. At this point, at this velocity point of 0, our man has stopped, and something's about to change. He will no longer be moving in the positive direction. Now our man is moving in the negative direction. His rate of change is still the same. 1 second later, his velocity is -1. 1 second later, his velocity is -2. 1 second later, his velocity is -3, and so on. Okay? So what this tells us is that we see that his velocity is decreasing for 5 seconds until it hits 0, and then it is increasing in the negative direction as he speeds up towards the left. Okay, so this is like you're running out of your house. You think you forgot your keys, so you start to slow down, and then you're like, yep, I forgot your keys. So you turn around and you start running back the other way. That's all that happened here. A couple things that's interesting about the position time graph, okay? For that very first second, he started at a position of 0. 1 second later, he's at a position of 4.5. So in the first second, he moved 4.5 meters. Then he went from 4.5 to a position of 8. He only moved 3.5 meters in that next second. So he first moved 4.5, then he only moved 3.5. That's why our curve is kind of starting to flatten out, is because the rate of change of position is decreasing. Which makes sense, because if we look at our velocity, which is the definition of is the rate of change of position, our velocity is decreasing as we get close to 0. Okay. Now, at that time, he's at a position of 12.5. 1 second later, he's at a position of 12. So he's moved in the negative direction, 0.5 meters. 1 second later, he's at a position of 11, or of 10.5. So he only moved 0.5 in the negative direction. Now he's moved 1 in the negative direction, 1.5 in the negative direction. Then he's going to move 2.5 in the negative direction, 3.5 in the negative direction. So after this midpoint right here, we would say the rate of change of position is increasing in the negative direction, which is a fancy way of saying our velocity is increasing in the negative direction. He's running even faster to the left. The last things I want to highlight, whenever something crosses the x-axis, it's interesting. On our position time graph, it crosses the x-axis at the beginning. That's where he started. But we also see he crosses the x-axis again later, which is when he gets back to 0. And then from there, he's just going to continue on in the negative direction for infinity. He's become a very negative man. All this time, our acceleration was always -1. Okay, wow, that was a lot. Let's clear it. Let's start it again. Let's put him at a position of 5, a velocity of 1, an acceleration of -1. Run it. Oh, sorry. I made it boring. Let me reset that. We got 5. Let's set it at a velocity of +5 and an acceleration of -1. Now let's run it. Why did he just stumble? I didn't want him to stumble. Position of 5. I think he's just tired of running, and that's what he's trying to tell me. There we go. Oh, it cleared my acceleration. Oh my gosh. I'm sorry, guys. One more time. Position of 5, velocity of 5, acceleration of -1. Okay. Positive position, positive velocity, negative acceleration. Here we go. Okay. Decrease in velocity. It's decreasing because it's getting closer to 0. He hits 0. So he's stopped. We can't see him. He's off the screen. He's stopped. Now he's coming back in the negative direction. Look at his position. His position is now decreasing. It's getting closer to 0. He's back on our screen. Here we go. He's about to cross the x-axis because he went past 0. And now he's going to continue on in the negative direction forever. So we have another bottom opening parabola. Bottom opening parabola. Our velocity decreased till it got to 0. Then it increased in the negative direction. His position, the graph looks exactly the same. The only difference is we shifted it up because our y-intercept was 5 where he started. Now for the last one, we're going to set our position negative, our velocity positive, our acceleration negative. Here we go. All we're going to get is a really clean parabola here. And it did not record my acceleration. Let's try this one more time. One day I'll get this down. Position of -5, velocity of 5, acceleration of -1. Okay, so there he goes. He's going, going, going. Notice what the velocity graph is doing. It is decreasing. It's getting dangerously close to 0. He's barely moving. Our velocity graph touches 0. He stops moving. Then it starts increasing in the negative direction, which means he has now turned around and he's starting to speed up to the left. He's not just moving to the left, he's speeding up to the left. our acceleration is a flat -1 value, and our parabola has curved down. We see two x-axis crossings, which makes sense because he went past the 0 mark once, then he passed it again right here. Okay? This represents pretty much all of the scenarios. The only thing that would be different is if, we already did positive acceleration, okay? Now, can you change all these numbers and get different things? Yes, I could give him a position of 0, a huge velocity of 10, and an acceleration of -1. 0, 10, -1, okay? All it's going to do is the exact same thing. Because the acceleration is negative, we're going to see that velocity decrease until it hits 0, which we're going to have to wait a little while for. Cue Jeopardy music. Okay, so he crosses the 0 at 10 seconds. Now I can predict it's going to take him exactly 10 seconds to get back to where he started. So keep an eye on that clock, and when it says 20 seconds, he should be passing by the 0 meter mark. If that's true, I'm officially a wizard. No, I'm a physicist. Same thing. Oh, there he is. He's back, and 20 seconds he crossed the 0. This is the power of understanding these graphs. You can start to predict the motion of objects by understanding these graphs and the relationships between them. I knew that it took him 10 seconds to get to 0. That's the point where he stopped and turned around, which means it should take him 10 seconds to get back to where he started because our acceleration was always the same. By increasing that velocity, all we did is we took our parabola and we stretched it really far apart, which is what made it more interesting. Okay. We also could come up with let's do something just one more time. Let's set his position back to 0. Let's set his velocity to some insane number like 300. But let's also set his acceleration to an insane number like -200. Now, I haven't tried this before. We'll see if it crashes the program. Here we go. Oh, there he goes. He's gone. And there he goes. He's back. He moved so quickly we couldn't even see him. Oh, no, there he goes. Now he's back. Okay, so you can't see it at all. It's all off the graph, but we basically had a huge increase and a huge decrease, and that's what we see on the graph here. Okay, so all it is those parabolas, bottom or top, velocity this way or this way, and then acceleration, flat lines. Hopefully this helps. Sorry it was a little lengthy. If you've watched to this point, give yourself 2 thumbs up and double pats on the back because, I mean, it's Thursday, it's in the evening. And if you have any questions on this, shoot me a message. Bye, guys.